Welcome to this session. First of all, today is a very auspicious day. Happy Ganesh Chaturthi, Vinayaka Chaturthi to all of you. So we will make use of this auspicious day by solving some very good problem and taking a step ahead in our preparation for GATE. So today is a very good day to take a step forward in our GATE preparation. So let's do that. So I welcome all of you to this quiz session on analog electronics. So it's going to be really analog is especially going to be fun because analog is beauty, analog is design, analog is fun. I request all of you to go to this link bit.ly/tga081e link to access this test. All of you kindly go to this, please. Please go to that. I will come on the live chat also to you people. I'm just saying hi to all of you on the live chat. So let's quickly look at the instructions for playing quiz. The quiz, I'm going to guarantee you full fun and entertainment in this quiz. It's going to be a lot of very special, tricky, interesting concepts. So what are the instructions? So there are no negative points, no need to worry. The moment there is no worry, we will put forth our best. So there is no negative point. All the quiz are going to be either a multiple choice question or it's going to be of NAT type of question. That's a numerical aptitude type of question. Okay. So you have to key in the number in case of NAT type of question, and you have to select the option in case of a multiple choice question. Only one option will be correct. Don't worry about that. And there are no negative points. So the questions, tougher the questions, more the points. The number of points per question will be displayed along with the question. And of course, there is benefit. There is prize for your smartness. If you're smart and if you're sharp and you're able to solve the problem quickly, faster you answer, higher you score. So I wish you all the best. Okay, let's get started with this. So let's wait for a couple of minutes so that everyone joins. Okay, welcome Bharat. Welcome Bharat. Let's wait for another couple of minutes for people to join. So in the meantime, as we are waiting for others to join, kindly discuss with me towards the end of the session whatever doubts you may have. I'll be more than happy to answer all your questions and doubts. That will be really, very helpful for uh, you as well as for me. It will be interesting. Couple of more minutes. 2 more minutes. We'll wait. Okay, let's start the quiz. So here comes the first question. Consider this analog circuit. The forward breakdown, there's a silicon diode, there's a germanium diode. The silicon diode has a forward breakdown of 0.7 volt. The germanium diode has a forward breakdown voltage of 0.3 volt. So they are asking which diode is forward biased, which diode is reverse biased. Very straightforward question, isn't it? But trust me, guys, these are all these questions appears to be straightforward, but it is not going to be straightforward. There is always a interesting cliche to all these questions. Let's see. Oh, none of them have answered correctly. Let's go further. Here comes the second question. There is a BJT given here. Beta is very large. VB on is 0.7 volt. VC sat is 0.3 volt. Which of the following is true? I think people are taking the bait. They are not able to get the correct answer. So these questions are very easy but tricky, I'll say that. Let's go to the next question. Consider the BJT circuit shown. Beta is very large. If RC is increased from 1 kilo ohm to 4 kilo ohm and then to, okay, I think people have answered and okay, let's go further. People are yet to open their account. Let's see here. The input voltage Vi is increases linearly from 0 to 150 volt. At what value of Vi will D1 turn on? Assume D1 and D2 are ideal silicon diodes. Oops. People are not answering correctly. 137.5 is the correct answer. Here comes the last question. Let's see if somebody answers this. So here you are being shown with a diode circuit. What and both the diodes are ideal diodes. How does the transfer characteristic V0 versus Vi will look? Strange, strange. Okay, let me stop sharing. Let me stop sharing this. Let us discuss the solution. The solutions are going to be very interesting here. I trust you. Okay, let's look at the. Okay, let's discuss the answers. The answers are going to be very interesting. So the first question goes something like this, correct? The first question was something like this. This is 5 volt and you have a 1 kilo ohm resistance, you have a silicon diode, then you have a 80 ohm resistance, then you have a germanium diode. The forward breakdown voltage of this is 0.7 volt and this is 0.3 volt. This is what is given. So let me call this as node X and let me call this as node Y. So I am going to assume both D1 and D2 are on. If both D1 and D2 are on, this is the way we will always solve the problem. Whenever we have diode circuits in operating with DC, assume both the diodes are on and solve it. If both the diodes are on, what you will see? This will be 0.7 volt. This will be like a battery of 0.7 volt. This will be like a battery of 0.3 volt. And there is a 80 ohm resistance. And there is 1 kilo ohm resistance here. And this is 5 volt. This is how the circuit will look like. Now, after this, I'm going to just apply Ohm's law. This is 5 volt. This is 0.7 volt. So the delta V is 4.3 volt. So 4.3 volt, 1K. What will be this current? I1 is nothing but 4.3K divided by, 4.3 volt divided by 1K, which is 4.3 milliampere. Or let me, okay, this is 4.3 milliampere. So I will put I silicon and I germanium, IS and IG. Okay, correct, because they are forward biased means the current will be conducted in this direction only. The diode cannot conduct in the reverse direction, correct? Now this is 0.7 volt. This is, let me say, I2. Now I2 is equal to 0.7 minus 0.3 divided by 80 ohms. So this is 0.4, 400 millivolt divided by 80 ohms, which is nothing but how much? 5 milliamperes. So 5 milliampere is I2. Now I2 is equal to IG, because I2 and IG are same, because they are in series, same current will flow. I2 equal to IG equal to 5 milliamperes. Now this is my node X, correct? At X, by Kirchhoff's current law, what will I get? I1 is equal to IS plus I2, which implies IS is equal to I1 minus I2, which means I1 minus I2 means how much? I1 minus I2. I1 is 4.3 minus 5, which is minus 0.7 milliampere. Diode cannot have negative current in forward breakdown. Correct. If you look at the VI characteristics of the diode, this is the forward breakdown, correct? So the diode current is positive, ID and VD. So the diode current is positive. The diode current cannot be negative here, correct? Correct. This is a PN junction diode characteristics, which implies assumption of D1 on is false. So only D2 is on. So what is effectively, this is 5 volt. Till here many people will solve correctly. Let me tell you. This is 1000 ohms. 1 kilo ohm is nothing but, and this is 80 ohms. This is 0.3 volt, and your silicon diode is off. So off means it's like a open circuit. This is the silicon diode. Now, here comes the most important point. Now, let's see. This is 5 volt. This is 4.3 volt. So the delta V is 4.7 volt. So the current here and here will be same because this current is 0. This current is 0. This current and this current will be same. I1 and Ig will be same. Since ID equal to IS equal to 0, I1 equal to Ig is equal to 4.7 divided by 1080. So how much this will be? 4.7 divided by 1080. Let us calculate. 4.7 divided by 1080, which is 4.35 milliamperes. 4.35 milliamperes. Now 4.35 milliampere passing through 1K. What will be the delta V? So therefore I 1 kilo ohm is sorry, voltage drop across 1 kilo ohm will be what? 4.35 milliampere into 1K, which is 4.35 volt, which means Vx is equal to 5 volt minus V 1 kilo ohm, which is 0.65 volt. See, so the voltage here is 0.65 volt. The voltage here is 0.3 volt. So now go back. What are the options given? Many people misunderstand this. So silicon diode, reverse bias, germanium diode, forward bias, silicon diode, forward bias, germanium diode, reverse bias. Both are reverse biased, both are forward biased. These are the options given, correct? 90% of the people select this. They think that silicon diode is reverse biased and germanium diode is forward biased. Why? Because silicon diode is off and germanium diode is on. But this is wrong answer. Here silicon diode is not reverse biased. Kindly note, VAK greater than 0, the anode to cathode voltage is greater than 0, the diode is forward biased. Look at this. The anode, this is the anode of the silicon diode, this is the cathode of the silicon diode. The anode is at 0.65 volt, the cathode is at 0. So VAK of the silicon diode is 0.65 volt, but it is less than V forward breakdown. So if you look at the characteristics of the diode, look at this region. This is the most important point. Look at this region. In this region, diode is forward biased, but it is it has not undergone forward breakdown. So from the biasing point of view, the diode is very much forward biased. The question is saying the diode is forward biased or not. The diode is forward biased. So both diodes are forward biased. This is the correct answer. This is the tricky question. Many people made wrong answers here. So please be very careful about this question. This is very important and interesting concept. Many people selected wrong option. Even when this question came in one of the exam, many people selected the wrong option for this question. So be very careful about these type of questions. See, this is what I am trying to tell you. The questions in gate will not be tough, it will be tricky. This question also came in one of the competitive examination. The options are really very cunningly given. So the question says beta is very large. VBE on is 0.7 volt. VCE sat equal to 0.3 volt. And they are given 4 options. What are the 4 options? The options are very cunningly given. This is transistor Q. Q is off. Option B says Q is on. Q is on, conducting 0.8 milliamperes. Q is on, conducting 1 milliampere. Q is on and VCE equal to 1.6 volt. So now let us look at this question. Many people, the options why I say it's cunningly given is many people think that VB equal to 0. For a NPN transistor, base is grounded, so the transistor will not work. So the transistor Q is off. Many people will go for this option, but this option is wrong. See, we should look at VBE. Please note VB. Look at VBE. VB equal to 0. Still, Q can be on if VBE equal to 0.7 volt is possible. Look at this. They have told VBE on is 0.7 volt. So now look at the circuit given. There is a minus 10 volt here. This minus 10 volt will pull down the voltage such that your VBE of 0.7 volt is possible. So this emitter voltage will be minus 0.7 volt because it can go negative. Why it can go negative? Because there is a minus 10 volt. That this minus 10 volt will cause the emitter voltage to go down such that VBE is 0.7 volt. Now with this, let us solve what happens. Now let us see what happens. Now if this is minus 0.7 volt, this is 0 volt, the delta V here is 0.7 volt. Now let me call this as E, let me call this as C. Now let me call this as RE because it's connected to emitter, and let me call this as RC. Now IRE is equal to, let me call this as IRE. This current flowing in this direction because this is at high, 0 is at higher potential, minus 0.7 volt is at lower potential, right? So this is IRE. So what is IRE? IRE is 0.7 volt divided by 1K, which is 0.7 milliampere. So 0.7 milliampere is coming here. Now this transistor is going to be the emitter current of the transistor IE. This current is 0.8 milliampere. So if I look at the transistor, let me redraw. It's like this, correct? This is your IRE. This is 1 kilo ohm. This is minus 0.7 volt, and this is 0.8 milliampere connected to minus 10 volt. The base is at ground, correct? I am looking at only this portion. Now by KCL at emitter, this current is the current coming out of emitter IE. IE is the incoming current. IRE is also the incoming current. Sum of incoming current is equal to the sum of outgoing current, 0.8 milliampere. Therefore IE is equal to 0.8 milliampere minus IRE, which is 0.8 minus 0.7, which is 0.1 milliampere. Okay, this is the IE. Okay, now let us look at the entire circuit. Now let us look at the circuit. So this is 0.8 milliampere, this is minus 10 volt, this is grounded, RE equal to 1 kilo ohm, and 0.7 milliampere is coming like this, 0.1 milliampere is coming like this. Now we have our collector circuit where I have 1 milliampere connected here, correct? 1 milliampere is connected. This is 1 kilo ohm. Now, what will be the collector current? What is the relation? IC, we know IC by IE is equal to alpha. And alpha, what is alpha? Alpha equal to beta by 1 plus beta. If beta is very large, alpha is equal to 1. That's what it means. That in the problem, they have told beta is very large. If beta is very large, alpha is equal to beta by 1 plus beta will be approximately 1. So alpha is 1. So therefore, IC is equal to IE. That's what is the meaning of beta if beta is very large. So what do I know? The collector current is also 1.1 milliampere. Now this is my collector by Kirchhoff's current law at C. Incoming current is 1 milliampere is equal to IRC. This is RC. IRC is also going out. IC is also going out of the node. So IC plus IRC, which implies IRC is equal to 1 milliampere minus 0.1 milliampere, which is 0.9 milliampere. So this IRC current is 0.9 milliampere. Therefore, VC, what will be VC? VC is what? Rather, I can say VC minus 0 divided by RC is equal to IRC, which is implies VC is equal to IRC into RC, correct? Which is nothing but VC is equal to IRC. What is IRC? IRC is 1 kilo ohm into 0.9 milli, which is 0.9 volt. See, throughout the problem, I am just applying Kirchhoff's current law and Ohm's law, nothing more than that. See, what is this current? IRC. IRC is nothing but this voltage is VC, this voltage is 0. So, VC minus 0 divided by RC is IRC. That's what I wrote here. VC minus 0 by RC is IRC. So, therefore, VC is 0.9 volt. Therefore, VCE is VC minus VE, which is 0.9 minus 0.7, which is 1.6 volt. So the transistor is on with a VC of 1.6 volt. Option D is the correct option. Clear? Option C is the correct option. Okay. Now the next question. The next question goes something like this. This is 5 kilo ohm. You have a VZB equal to 5 volt. 4.3 K. Beta is very large. VB on equal to 0.7 volt. VCE sat equal to 0.7 volt. Correct, 0.7 volt is what is given, right? Yeah. And we have RC, which is 1 kilo ohm, and this is connected to 12 volt. Now what they are saying, RC is increased from 1 kilo ohm to 8 kilo ohm. So you are going through steps 1 kilo ohm to 4 kilo ohm, 4 kilo ohm to 8 kilo ohm, like that. You are increasing the RC. What happens is the question. Now, first of all, what is this circuit? Let us understand what is this circuit. Can anybody tell me what is this circuit? Can anybody tell me what is this circuit? Let's see, what is this circuit? What is this circuit? Take a quick guess. Analyze it. What is this circuit? Yes, this circuit is a current source. Look at this. This voltage is at 5 volt. Because of Zener diode, this voltage will be at 5 volt. VB on is 0.7 volt. That means this will be at 4.3 volt. This is 0 volt. So 4.3 volt, 4.3 K. How much current will come? 1 milliampere will be the current coming. Correct. Therefore, IE is 1 milliampere. Why it is fixed? Because VB equal to 5 volt and VBE equal to 0.7 volt. VE is fixed at 4.3 volt, which implies IE is equal to VE divided by RE, which is 4.3 divided by 4.3 K, which is 1 milliampere. This is fixed. And beta is very large. Beta is very large means IC equal to IE, which implies IC equal to 1 milliampere. That means we are fixing IC without even knowing RC. This is constant current source, correct? That is irrespective of RC, as long as the Q is in active region, IC is fixed at 1 milliampere. This is the most important point. Whatever may be the value of RC, as long as the transistor is in saturation region, the current through RC is fixed at 1 milliampere, because I am estimating the current through RC without even knowing what is RC. Correct. This is my IC. IC is fixed. Why IC is fixed? Because VB is fixed, VBE is fixed, so VE is fixed, VE is fixed, RE is fixed, IE is fixed, IE is fixed, IC is fixed. That's the way the circuit works. Clear? So this is a constant current source. Now we need to look at what they are saying. Now they are going to, but this circuit will not work for any value of RC. This will work as long as Q is in saturation. This is the most important point. As long as Q is in active region. So what is the limiting point of the circuit? So what is the limiting point of the circuit? Please note. So this voltage is VC. So VC equal to VCC minus ICRC implies as RC is increased, VC is equal to VCC minus ICRC. If RC increases, IC is fixed, but IC is fixed. So what will happen? This implies as RC increases, VC will go down because VCC is fixed. See, VCC is fixed at 12 volt. Now I keep on increasing RC. So the drop across RC will keep on increasing. So VC is VCC minus ICRC. So VC voltage will start coming down. But okay, VE is fixed. VE is fixed at 4.3 volt. Why 4.3 volt? Because VB is fixed by Zener Diodes. VB is fixed by Zener diode at 5 volt. Because the base voltage is fixed at 5 volt, the emitter voltage is fixed at 4.3 volt. So emitter voltage is fixed, but VCE is coming down. Therefore, VCE reduces as RC increases. But VCE cannot go below VCE sat. This will be the limiting point of the circuit. So, what is the VC at saturation? VCE will be equal to VCE sat equal to 0.7 volt. Therefore, VC will be VE plus VCE sat, which is 4.3 plus 0.7, which is 5 volt. Therefore, RC will be what? VCC minus VC divided by IC, which is 12 minus 5, and we are fixing IC at 1 milliampere. So 7 divided by 1 milliampere, which is 7 kilo ohm. This is the max value of RC. So for RC greater than 7 kilo ohm, Q will enter saturation and IC will drop. So the correct answer is till 7 kilo ohm, IC will remain constant even if RC is varied. Beyond that, Q enters saturation and IC will drop. This is very important. I hope these concepts are very clearly understood. These are all very, very important concepts. Okay, we'll go to the next problem. The next problem goes like this. So Vi varies linearly from 0 to 150 volts. D1, D2 are ideal diodes. At what value of Vi will D1 turn on? This is the question. So let us solve this. First, let us understand at what value of Vi will D2 turn on? The answer is 25 volt. Why? Because diodes are ideal diodes implies VAK greater than 0, even that is VAK equal to 0 plus, just above 1 millivolt, 0.1 millivolt also sufficient, the diode will start conducting. Diode starts conducting. This is the most. If it's a silicon diode, then only it will need zero point 0.7 volt. If it's an ideal diode, even for just a 0.1 millivolt forward bias also, it will start conducting. That's what is an ideal diode. And it will stop conducting in the reverse direction, even for 0.1 millivolt. Correct. That's what is the ideal diode behavior. So the moment the input voltage goes beyond 25 volt, this is a linearly increased from 0 to 150 volt. Correct. It is being raised linearly from 0 to 150 volt. At what value of Vi will D1 turn on? The moment Vi crosses 25 volt, this is 25 volt plus. This is 25 volt. So no current flows because no, the diode, ideal diode starts conducting with zero current. So no current flows. So this voltage will be 25 plus, this voltage will be 25. So the diode D2 starts conducting. So clearly D2 starts conducting. When D2 is turning on, there is no current flowing in the circuit. This is the most important point. This is the most important point to note in this question. When D2 is turning on, there is no current because D1 is definitely off. You need more than 100 volt to turn on. So fine. All this X and Y. Now, when observe, kindly observe, this is very, very important. What D2 wants is Vy greater than 25 volt. See, this is a very important point. Observe this. What D2 wants is Vy greater than 25 volt, which implies Vi greater than 25 volt as well, because D2 turns on consuming zero current. D1 is off. So net current in the circuit is 0, which implies Vy equal to 25 volt imply Vi equal to 25 plus volt, because no current flows anywhere. No current flows anywhere. The drop years are negligible. The drop here are, there is no drop here, there is no drop here. The entire whatever is this voltage, the same voltage is available at Vi also. Whereas when V1 is turning on, sorry, when D1 is turning on, D2 is already on and conducting. Though D1 turns on consuming zero current, the current in the circuit is not zero as D2 is conducting. See, all these points you should keep in mind. Then only you will be able to solve the problem. You should be able to analyze all these things. When D1 turns on, D2 is already on and conducting. So let's see what will happen. What is the picture when D1 is turning on? So when D1 is turning on, the picture will look like this. This is 100K. This is D1. This is 100 volt. This is 200K. D2 is already on. So D2 is like a short circuit. This is 25 volt. Now for D1 to turn on, we need Vx greater than 100 volt. Correct. So this is, that is 100 volt plus, just above 100 volt. So let us keep it as 100 volt itself. Now this is 100 volt. Now this is 25 volt. This voltage is 75 volt. So therefore V 200K is 75 volt, which implies I 200K will be V 200K divided by 200K, which is nothing but 75 volt divided by 200K, which is 375 microamperes. Now I1 equal to ID1 plus 375 microamperes. ID1 will be 0 when D1 is turning on. Therefore, I1 equal to 375 microamperes when D1 is turning on, which implies Vi equal to Vx plus this drop V100K, which is 100 plus 375 microamperes into 100K, the drop across 100K, correct? Which will be 100 plus 137.5 volt. So just 137.5 volt. Therefore, at Vi equal to 137.5 volt, D1 will turn on. This is the most important point. Clear? Now guys, many people they think that because of 100K and 200K there is a huge voltage drop. That is not the point. Kindly note. Example, if this is my Vi, say Vi is varied from 0 to 150 volt. I have the same 100K resistance, D1, 100 volt battery. If this is the circuit, in this circuit D1 turns on at Vi equal to 100 volt. Why? Because there is no other path. Because there is no other current flowing through 100K when D1 is turning on. See here, I want this voltage to be 100 volt. When this voltage is 100 volt, this voltage is also 100 volt because diode D1 turns on consuming zero current. So when the current flowing here is zero, this is 100 volt is same as this being 100 volt. Whereas in the previous circuit, there was already a current which is going in the other path. So even though the diode current was zero, the other path current was 375 microampere. And that current was flowing through 100K, which was causing a 37.5 volt drop. So kindly note, it is not the 100k. Many people get confused that because of 100k there is a drop. Because of 100k there is a drop, but not always. In this circuit also 100k is there, but there is no drop here when the D1 is turning on. Because the diode turns on consuming zero current. The main problem or the main point in the previous circuit is when D1 is turning on, D2 is already on, and the current whatever is flowing through D2 flows through this 100k also, which is causing a drop of 37.5 volt and preventing this D1 from turning on. Clear? This is very, very, very important. Clear? Okay. Okay. The last problem. D1, D2 are ideal silicon diodes. Okay. V0 versus Vi transfer characteristics they are asking. How V0 versus Vi will look. Now let us look at this. And it's given that Vi equal to 24 sine some thousand pi t volts. I am least bothered about this number. Vi is 24 sine omega t. So Vi is a sine wave of 24 volt. Okay, this is my Vi. So it's a sine wave of 24 volt. Now let us note, what are the note? If D1 turns on, if D1 turns on, V0 is 3 volt. If D2 turns on, V0 equal to minus 3 volt. Correct. For D1 to turn on, Vi should be greater than 3 volt. Correct. Because we are looking for VAK to be positive. Correct. So Vi should be greater than 3 volt. This voltage should be greater than 3 volt. That means Vi should be greater than 3 volt. Then only D1 can turn on. Correct. And for D2 to turn on, Vi should be less than minus 3 volt. Then only VAK will be positive because anode is at minus 3 volt. So for D2 to turn on, Vi should be less than 3 volt. Clearly, D1 and D2 cannot turn on simultaneously. Correct. Clearly, D1 and D2 cannot turn on simultaneously because in one case you need greater than 3 volt, one case you need less than 3 volt. Correct. If both D1 comma D2 are off, V0 will fall. If both V0 Vi are off, see, let us draw that. See, this is my Vi, this is my R. If both V0, both D1 and D2 are off, I have a 3 volt here, I have 3 volt here. Both D1 and D2 are off, V0 will be equal to Vi, correct? If D1 is on, this is D1, D2 off. If D1 is on, D2 is off. D1 on. So D1 on means diode is short. D2 is off. So V0 is 3 volt. Correct? This is 3 volt. This is shorted to 3 volt. So whatever is the difference between Vi and 3 volt will drop across this resistance. And this is Vi. D1 is off. D2 is on. D2 is on means D2 is like a short. And I have minus 3 volt here. So V naught equal to minus 3 volt. Whatever is the difference between V naught and Vi will drop across this resistance. So for this Vi should be greater than 3 volt. For this Vi should be less than 3 volt. And for this minus 3 is less than or equal to Vi is less than or equal to 3 volt. So between 3 volt and minus 3 volt of input, V naught will follow Vi. Beyond 3 volt, V naught will be clipped to 3 volt. This is what is the behavior we are seeing. So if I now if I represent this as a transfer characteristics, what will I see? This is my Vi, this is my V naught. So this is my minus 3 volt, this is my plus 3 volt. Between Vi values of minus 3 and plus 3, V naught will simply be equal to Vi. So that is like a straight line passing through origin. Beyond, when Vi is more than 3 volt, V naught is fixed at plus 3 volt. When Vi is less than minus 3 volt, V naught will be fixed at minus 3 volt. So this is the transfer characteristics. And what is this circuit? This is a bidirectional shunt clipper. And since it is clipping at equal voltages, it's also a bidirectional symmetric shunt clipper. Okay, this is the solution for all the 5 problems. Okay, so I hope all these problems are clear. I hope all these problems are clear. Okay, thank you everyone. Thank you. Happy Ganesh Chaturthi once again. Thank you. Bye.